January 1944. A bitter wind cut across the snow-covered testing grounds in Peenemünde, Germany. The faint glow of molten metal reflected off frost-crusted equipment. Engineers huddled in their wool coats, notebooks clutched tightly, eyes fixed on a strange, towering device that hummed with an almost otherworldly energy. Soldiers shifted uneasily, unsure whether to admire the creation or fear it. For years, whispers of an impossible weapon had circulated through scientific circles and military halls. Alike critics had scoffed, calling it a fantasy, a mockery unworthy of serious attention. And yet here it was, steel and fire, shaking the very ground with each test ignition. The air was thick with anticipation, the smell of burning propellant and scorched earth lingering in frozen nostrils. No one spoke of the destruction this machine could unleash. Not yet. Even the engineers, their faces pale under the dim light, understood that this was not merely a test of technology, but a glimpse into a new era of warfare. The impossible was becoming real, and in the next hours, its roar would echo far beyond these frozen fields. This weapon's story did not start here, nor with the test. It began years earlier, in a world driven by fear, ambition, and the relentless search for ultimate power. By the early 1930s, Europe was a continent still haunted by the scars of the Great War. Trenches had dried, but the memory of devastation lingered in the minds of soldiers and civilians alike. Nations rebuilt their militaries cautiously, yet the shadow of technological escalation loomed over every armaments program. Germany, constrained by the Treaty of Versailles, sought ways to regain strategic superiority without drawing immediate international scrutiny. Amid these geopolitical tensions, the concept of superweapons began to capture the imagination of scientists and military planners. Engineers experimented with rocketry, chemical propulsion, and explosive ordnance, pushing physics to the edge. At the time, many considered certain designs impossible: machines too large to transport, fuels too volatile to handle, guidance systems too primitive to control. Yet, the very implausibility of these weapons made them irresistible to a military leadership desperate for an edge. In laboratories and hidden facilities across Germany, small teams of physicists, engineers, and mechanics worked in near secrecy. Peenemünde, on the Baltic coast, became the epicenter of this ambition. There, under the direction of visionary engineers, prototypes were drawn on drafting tables with meticulous precision. Calculations covered chalkboards from floor to ceiling. Equations that seemed abstract but were the blueprint for instruments of mass destruction. Simultaneously, intelligence reports from foreign powers suggested that rival nations, Britain, France, and the Soviet Union, were exploring similar high-risk projects. This sense of urgency fueled the German military-industrial complex. Skeptical officers demanded proof before allocating resources, while scientists pressed forward, confident in their calculations, aware that failure could mean disgrace, but success could redefine warfare. By 1938, several experimental weapons had been tested, producing mixed results. Missiles veered off course, explosive devices detonated prematurely, and prototypes collapsed under their own weight. Each failure was met with derision in some quarters. The so-called impossible weapons were a joke, a costly obsession. Yet, with each setback, knowledge grew. Engineers learned to stabilize fuel mixtures, reinforce structural integrity, and fine-tune propulsion. The impossible became plausible, one incremental improvement at a time. Political pressures compounded scientific urgency. Adolf Hitler, enthralled by technological innovation and obsessed with delivering a weapon capable of decisive results, personally endorsed several projects. His interventions accelerated research timelines and elevated the stakes. Military planners, once cautious, were now bound to deadlines dictated by both political ambition and the looming threat of Allied intervention. By late 1939, Germany had invaded Poland, igniting the global conflict that would become World War II. The battlefield was no longer theoretical. Every technological advantage mattered. Armies faced mechanized infantry, rapid-fire artillery, and advanced aircraft. Highlighting the limitations of conventional weapons, commanders increasingly looked to revolutionary concepts, weapons that could bypass traditional defenses, strike from unexpected angles, and alter the calculus of war. Within this environment, the impossible weapon concept transitioned from fantasy to a tangible goal. It was no longer a mere engineering challenge. It became a strategic imperative. Laboratories and testing grounds buzzed with activity. Scientists worked in shifts, fine-tuning components, measuring exhaust velocity, and calculating destructive yield. Soldiers observed the tests, taking notes on blast radius, recoil, and deployment feasibility. Every success emboldened leadership. Every failure offered lessons that could not be ignored. By 1940, a growing consensus emerged, while skepticism remained. The weapon's potential to transform the battlefield was undeniable. The stage was set for an innovation that had once been mocked, a device that promised to turn ridicule into one of the most feared instruments of mass destruction in human history. This careful nurturing of science under wartime pressure would soon collide with the reality of deployment, marking the first steps toward a weapon whose name would echo across continents and decades. By 1941, the war had spread across Europe, and the stakes for Germany had never been higher. Blitzkrieg campaigns had initially overwhelmed Poland, France, and the Low Countries, but the longer the conflict stretched, the more the limits of conventional weapons became apparent. Tanks bogged down in mud, artillery struggled to breach fortified positions, and aircraft faced increasingly sophisticated anti-aircraft defenses. Commanders realized that decisive, technologically advanced solutions were no longer optional, they were essential. It was in this climate of urgency that the so-called impossible weapon gained unprecedented support. The German High Command began allocating resources and manpower at a scale previously reserved for strategic bombers, and U-boat production engineers were no longer working in isolated labs. Entire factories were repurposed for research, assembly, and testing. Supply chains were overhauled to deliver rare metals, specialized fuels, and high-precision instruments, all of which had previously been considered scarce or too difficult to handle. Development proceeded in stages. Early prototypes were tested under controlled conditions, often in remote sites like the forest of Thuringia or along the Baltic coast. Each test produced invaluable data. Misfires revealed flaws in fuel mixtures. Guidance systems were calibrated against unpredictable wind patterns, and explosive yields were measured with increasing accuracy. Soldiers and technicians who witnessed these trials spoke of awe mixed with trepidation. Machines that had once been dismissed as fantasy now demonstrated terrifying potential. Meanwhile, intelligence reports from the Allies began to hint at unusual German experiments. British and Soviet operatives speculated on new long-range weapons, yet few could anticipate the scale or destructive capacity of what was being developed. In some circles, the German effort was still dismissed as improbable, a mad scientist's folly. This underestimation would prove pivotal when the weapon transitioned from the testing grounds to the battlefield. Political pressure continued to accelerate development. Hitler's direct involvement meant deadlines were strict, and the margin for error vanished. Engineers often worked around the clock, aware that success or failure could influence the course of the war itself. Ethical considerations were secondary. The focus was purely functional, a weapon that could break enemy morale, destroy fortified positions, and shift the strategic balance. By mid-1942, several working models had been constructed, though still imperfect. These early versions were capable of demonstrating the principle, a weapon that could deliver destruction in ways conventional artillery could not. Reports emphasized speed, accuracy, and explosive yield, each metric carefully compared against the performance of existing weapons. Commanders began incorporating these findings into operational planning, imagining how the impossible could be used in campaigns against Britain, the Soviet Union, and beyond. At the same time, the human dimension of this development was clear. Scientists wrestled with unprecedented technical challenges. Soldiers trained with unfamiliar machinery, and officers debated tactical deployment. Fear and fascination coexisted. Fear of the weapon's destructive potential, fascination with its unprecedented engineering. This duality, admiration for human ingenuity, tempered by the horror of its application, would define the narrative of the weapon throughout the war. By 1943, the line between prototype and battlefield-ready device was being crossed. Tests were increasingly realistic, simulating urban targets, bunkers, and enemy formations. Data was meticulously recorded, analyzed, and applied to successive iterations. What had begun as a speculative experiment, mocked by skeptics and derided by traditionalists, was now on the cusp of operational deployment. The context was set: a world at war, a nation under pressure, and a technological marvel that had once been called impossible. All the elements, the science, the leadership, the urgency converged to create a weapon capable of altering the course of battles, from skepticism to preparation. The stage was ready for the angles that would reveal the true nature of this unprecedented force. The impossible weapon was not a single genius's creation, nor the product of a solitary factory. It emerged from the minds of dozens of engineers, physicists, and technicians, each driven by curiosity, ambition, and a profound sense of historical urgency. Wernher von Braun, often the most visible figure in public records, was only one of many who wrestled with equations that could dictate life or death on a continental scale. These scientists labored under extraordinary pressure. Daily schedules blurred into nights of calculations and tests. Mistakes were costly, not only financially, but in personal and professional reputation. Early failures were met with ridicule. Peers labeled prototypes foolish or fantastical, yet the engineers persisted, motivated by a combination of scientific pride and the understanding that success could redefine the battlefield. At testing grounds, soldiers observed the strange machines with a mix of awe and dread. Some whispered of magic, others of a terrible engine of death. The engineers themselves often appeared detached, eyes fixed on instruments and dials, hands precise, movements rehearsed. The human story was one of obsession, the tension between brilliance and the fear of destruction. Many questioned the morality of what they were building, but few could deny the thrill of creating something that defied conventional limits. From the outset, military strategists envisioned this weapon not as a replacement for conventional artillery, but as a force multiplier. Unlike conventional weapons, which relied on numbers and proximity, the new device promised speed, range, and psychological impact. Commanders imagined breaching enemy lines without prolonged siege, striking fortified positions without infantry exposure. The tactical advantage was clear. Shock and awe could disorient opponents, forcing retreats, sapping morale, and disrupting coordinated defense. Training exercises simulated scenarios in which a single strike could topple key infrastructure, sever supply lines, and create opportunities for rapid mechanized assaults. High-ranking officers debated deployment strategies with intensity, weighing the weapon's destructive capacity against logistical challenges and the risk of misfire. Yet the tactical potential was only theoretical until rigorous field tests demonstrated its feasibility. Engineers and soldiers noted how blast patterns differed from conventional explosives, how shock waves could penetrate bunkers, and how the speed of delivery created new possibilities for combined arms operations. The weapon's promise was a profound shift. The battlefield itself could be reshaped not by sheer numbers, but by precision and unprecedented destructive power. Technologically, the weapon pushed the boundaries of 1940s engineering propulsion. Systems were tested to limits previously considered impossible. Fuel compounds refined for stability, and guidance mechanisms calibrated against unpredictable environmental factors. Each component demanded innovation. Metallurgy had to withstand extreme heat and pressure. Electronics had to process information in milliseconds. And explosive payloads had to deliver maximum impact without premature detonation. Engineers meticulously documented each iteration. Failures were dissected with almost surgical precision. A misaligned nozzle or a faulty fuse could ruin months of work. Yet each setback provided data that made subsequent tests more accurate. By 1942, prototypes demonstrated that the impossible was achievable. Field observations confirmed theoretical models. Velocity, trajectory, and yield all aligned closely with predictions. The technological story was as much about human ingenuity as it was about raw machinery. Each breakthrough combined theory and practice, imagination and calculation, daring and caution. The weapon's design represented the apex of wartime engineering, a fusion of science and strategy that few outside Germany could fully comprehend at the time. No weapon, however revolutionary, becomes reality without decisive leadership. In the case of the impossible weapon, Adolf Hitler's personal fascination played a pivotal role. His interventions accelerated timelines, redirected resources, and prioritized the program above many conventional military projects. High-ranking officers, some skeptical, often deferred to his enthusiasm, granting engineers freedoms rarely afforded in wartime programs. Military leadership faced a delicate balance, embracing innovation without jeopardizing broader campaigns. Commanders debated whether to allocate limited manpower and materials to a weapon still considered experimental. Some viewed the investment as reckless. Others recognized that success could alter the course of the war. These decisions were not abstract. They determined the pace of testing, the scale of production, and ultimately, whether the weapon would transition from laboratory to battlefield. Leadership also influenced operational planning. Field commanders studied test reports, observed simulations, and incorporated the weapon into attack strategies. Decisions on deployment timing, target selection, and coordination with infantry and air support required trust in both the technology and the teams behind it. Miscalculation could render the weapon useless or even endanger friendly forces. For the Allies, intelligence on the weapon was fragmentary and often dismissed as exaggeration. Reports mentioned unusual rocket tests, large-scale explosions, and secret facilities. Yet few analysts grasped the scale or potential. British and Soviet intelligence noted anomalies, but conventional wisdom held that a weapon of such complexity could not function reliably in combat. This underestimation proved costly. Early deployments shocked enemy soldiers and commanders alike, revealing vulnerabilities previously unconsidered. Conventional defenses, bunkers, artillery emplacements, and fortified supply lines were suddenly exposed to unprecedented destructive forces. The psychological impact was profound. Fear and uncertainty spread faster than any physical damage. Commanders had to reconsider strategy, reallocating forces and resources to mitigate threats that had once seemed improbable. Enemy responses evolved slowly. Countermeasures were devised, but the combination of speed, range, and novelty gave the weapon a temporary tactical edge. This period of surprise highlighted the asymmetric advantage of technological innovation in warfare. A single breakthrough could ripple across entire theaters, forcing adaptation and reshaping engagement rules. Beyond strategy and mechanics, the weapon posed profound moral questions. Engineers and military planners alike faced the unsettling reality of what they were unleashing. Unlike conventional weapons, its scale and precision made indiscriminate destruction possible, challenging traditional rules of engagement and moral codes. Debates were subtle yet persistent. Should science serve pure function, or should it be restrained by ethical limits? Within the German scientific community, some privately expressed unease, recognizing that their calculations could result in massive civilian casualties. Military leadership, however, prioritized results over reflection, framing the weapon as a necessary instrument of national survival. The moral dimension added tension to the narrative of innovation. It illuminated the duality inherent in human ingenuity, the capacity to create tools of astonishing precision, and the equally real capacity to inflict catastrophic harm. The impossible weapon was a crucible, testing not just the limits of technology, but the limits of conscience in wartime. September 7, 1944, London woke to a sky streaked with fire. From afar, citizens could see trails of smoke as the first operational strikes of the impossible weapon ripped through the city. Air raid sirens wailed. Yet traditional anti-aircraft guns were powerless. The new weapon required no flight path over defenders, no careful trajectory through conventional corridors. It descended with precision, delivering destruction in ways previously unimaginable. The operational debut had been meticulously planned. German commanders selected London for both symbolic and strategic reasons. The city's industrial centers were vital to the Allied war effort, and its psychological significance could not be overstated. Units trained for weeks, synchronizing timing, calibrating fuel loads, and refining deployment techniques. The weapon's unique design allowed rapid launches from mobile platforms, making interception nearly impossible. Witnesses described a surreal scene: buildings crumbled, streets fractured, and debris littered avenues once bustling with life. Yet the most remarkable aspect was the shockwave of fear citizens had never encountered. A weapon that could strike seemingly at random, bypassing conventional defenses entirely. Military observers noted the tactical implications immediately. Conventional fortifications and defensive strategies were obsolete against this new threat. Back in Germany, the test engineers monitored results via film and telemetry. Their months of calculations had translated into reality. Early prototypes, once dismissed as fantasy, now demonstrated full operational capacity. Reports quantified devastation: bridges destroyed, factories rendered unusable, and thousands of civilians displaced or worse. These numbers were grim, yet they were only the beginning. Commanders on both sides recognized that the battlefield itself had changed. Allies scrambled to adapt, implementing early warning protocols and dispersing critical infrastructure. Yet the psychological impact outpaced material measures. Fear became a strategic tool, as powerful as any weapon. Soldiers in the field observed the effects, realizing that traditional engagements would require reconsideration. The event marked more than a tactical breakthrough, represented a fundamental shift in warfare. The impossible weapon, born of skepticism and human ingenuity, had crossed the threshold from theory to reality. It was no longer a laboratory experiment or a political gamble. It was a tangible, deployed force capable of altering campaigns and challenging conventional strategies. Behind the scenes, engineers prepared for subsequent launches. Data from this first operational use informed refinements, improving accuracy and destructive yield. Each deployment was studied meticulously: the trajectory of explosions, the dispersal of shrapnel, the structural vulnerabilities exposed. The combination of observation, analysis, and rapid iteration reflected the systematic approach that had brought the weapon from impossible concept to battlefield reality. As the dust settled over London, military planners understood that the war had entered a new phase. Success was measured not just in destroyed infrastructure, but in the strategic advantage conferred by innovation. The first operational strikes were a proof of concept writ large. The impossible had been achieved. Yet the moment also carried profound consequences. Civilian populations bore the brunt, ethical questions loomed, and the Allies faced urgent pressure to respond. This was only the beginning, a turning point that would escalate both destruction and ingenuity in equal measure. By late 1944, The weapon had evolved from experimental deployment to full-scale operational integration. Launch sites across northern France and the Low Countries were fortified, camouflaged, and synchronized to deliver a sustained campaign of strikes. The operational tempo increased, demonstrating not only the weapon's destructive potential, but also its strategic flexibility. The Allies faced a daunting reality. Intelligence reports initially underestimated both scale and accuracy. By the time reconnaissance confirmed repeated launches, the weapon had already disrupted critical supply lines, destroyed bridges, and damaged industrial complexes for soldiers on the front lines. The traditional rhythm of battle advance, hold, counterattack was shattered. Troops were forced to disperse, fortify hastily, and confront a threat that could strike without warning or apparent pattern. One of the most significant strikes occurred on Antwerp in late October 1944. The port, vital for Allied logistics, came under attack. The weapon's impact was devastating. Cranes toppled, warehouses obliterated, and docked ships rendered unusable. Commanders scrambled to reroute supplies, and engineers worked feverishly to repair damaged infrastructure. Beyond physical destruction, the psychological effect on personnel was immediate. Fear and uncertainty spread faster than word of mouth could convey. German reports emphasized operational success with clinical precision. Launches were timed for maximum effect, trajectories calculated to circumvent defenses, and data from each strike fed back into subsequent operations. Engineers refined guidance systems, adjusted propellant mixtures, and modified payloads to increase destructive efficiency. By the end of 1944, deployment had become routine. The weapon was no longer experimental, it was a central component of the German war strategy. Yet the operational success came at a cost. Logistical demands for fuel, specialized materials, and trained personnel were immense. Launch crews endured grueling schedules under constant threat of Allied reconnaissance and air attacks. The scale of coordination required between engineers, military planners, and field units was unprecedented, illustrating both the weapon's power and the fragility of the system sustaining it. For the Allies, countermeasures evolved. Too slowly, anti-aircraft batteries, radar systems, and conventional interception strategies proved largely ineffective. Attempts at sabotage or preemptive strikes against launch sites were partially successful, but could not fully neutralize the threat. Tactical adaptations included dispersing key assets, decentralizing command, and accelerating repairs. But none could entirely negate the psychological impact of a weapon that could strike at will. By December 1944, the cumulative effect was undeniable. Cities scarred, supply chains strained, and the calculus of battle irrevocably altered. Allied planners began intensive research into counter-technologies, accelerating their own missile and detection programs. The war had entered a new phase where technological ingenuity dictated not only who held the advantage, but also who could survive unscathed in an environment where conventional defenses were increasingly obsolete. The weapon's decisive deployment demonstrated a rare convergence of human innovation, technological mastery, and strategic foresight. What had begun as skepticism, mockery, and disbelief now dominated the battlefield. The impossible had been realized in full measure, reshaping both immediate tactical decisions and long-term strategic planning. As 1945 approached, the implications were clear. The war would not simply be fought with infantry and artillery. It would be defined by who could harness, deploy, and if necessary, counter the unprecedented destructive capabilities of technology. The turning point had been reached. The impossible weapon had claimed its place in the annals of history, leaving destruction in its wake and compelling both sides to adapt or be overwhelmed. The immediate consequences of the weapon's deployment were staggering. London, Antwerp, and other targeted cities bore the marks of devastation. Collapsed buildings, fractured streets, and scorched infrastructure. Casualty figures were sobering. Thousands of civilians were injured or killed. While industrial losses hindered production and logistics, entire neighborhoods were reduced to rubble, leaving survivors to navigate chaos amid lingering fear. Military assessments highlighted a different, though equally significant, dimension: operational disruption, key supply routes, bridges and transport hubs were rendered unusable, slowing troop movements and creating logistical bottlenecks. Commanders had to adapt on the fly, often improvising solutions to maintain the momentum of campaigns. The weapon's psychological impact was immediate. Soldiers reported an almost primal fear when news of new strikes arrived, and civilians struggled to comprehend an enemy capability that could bypass all conventional defenses. Official German reports celebrated the weapon's success with precise documentation. Telemetry data confirmed accuracy, destructive yield, and efficiency of deployment. Field commanders lauded its tactical value. One well-placed strike could neutralize multiple conventional units or destroy infrastructure that previously required sustained bombardment. Engineers and technicians, who had labored under intense pressure for years, now witnessed the tangible fruits of their work. What had been theoretical became reality, and its effectiveness exceeded even optimistic projections. Yet the aftermath was not solely strategic. The moral implications weighed heavily, particularly among engineers and some military officers. The scale of civilian casualties, the indiscriminate nature of destruction, and the weapon's psychological terror provoked quiet debates. Recorded in diaries and private correspondence, the impossible device had become an undeniable force of mass destruction, raising questions that would echo long after the war ended. Meanwhile, Allied forces began to reassess the nature of modern warfare defensive protocols. Previously built around conventional artillery, infantry formations, and early radar systems, were no longer sufficient. Engineers and strategists accelerated the development of countermeasures, dispersal of key assets, fortification of critical infrastructure, and research into interception technologies. Yet the pace of adaptation could not match the initial shock and destruction wrought by the weapon. In military journals and post-strike reports, the consensus was clear. The weapon had rewritten the rules of engagement. Its successful deployment validated years of research, experimental trials, and meticulous planning. The transformation from impossible concept to operational reality marked a turning point not just in specific battles, but in the broader strategic landscape of the war. The immediate aftermath demonstrated the dual nature of the weapon's impact: tactical advantage and human cost, operational success and ethical quandary. The world had witnessed the terrifying power of innovation harnessed for destruction, and the lessons learned would reverberate through military doctrine, engineering, and wartime ethics for decades to come. As 1945 began, the broader consequences of the weapon became increasingly apparent. Beyond immediate destruction, it reshaped military strategy across both fronts. Allied forces scrambled to adapt, developing countermeasures that ranged from dispersing troops and critical supplies to reinforcing industrial hubs and improving early warning networks. The weapon had exposed the vulnerability of even the most fortified positions, demonstrating that technological innovation could outpace traditional defensive doctrines. The psychological toll extended far beyond the battlefield. Civilians lived under constant fear of sudden strikes, and morale in occupied territories wavered under the specter of unprecedented destruction. Soldiers faced a new kind of uncertainty. Engagement was no longer solely a contest of numbers or tactics, but of who could anticipate and survive the deployment of weapons that defied conventional understanding. Letters and diaries from the period reveal anxiety, disbelief, and a growing awareness that the nature of war had irrevocably changed. Strategically, the weapon influenced subsequent campaigns. German command incorporated it into larger operations, coordinating launches with ground offensives to maximize disruption. Meanwhile, Allied planners accelerated research into comparable technologies, recognizing that the future of warfare would hinge on both developing and countering these innovations. Post-war programs, from missile development to early rocketry, drew directly from the lessons of the weapon's operational deployment, confirming its lasting influence on military science. The scale of destruction also prompted reflection within Germany. Engineers and commanders grappled with the duality of their creation, a technological marvel capable of reshaping battlefields, yet simultaneously a tool of indiscriminate devastation. While political leadership emphasized tactical success and propaganda value, those involved in design and testing were acutely aware of the ethical implications. This tension underscored a central theme of wartime innovation. Human ingenuity could achieve unprecedented feats, but at profound moral and societal cost. By mid-1945, the weapon's role in the war was undeniable. Cities bore scars. Supply networks had been disrupted, and traditional defenses had been proven inadequate. The Allies' ability to adapt limited further damage. But the lessons were indelible. Historians would later note that the weapon accelerated shifts in warfare, moving it toward an era dominated by technology, psychological impact, and strategic precision rather than sheer manpower. Ultimately, the weapon's aftermath extended beyond physical destruction. It reshaped the mindset of military planners, engineers, and civilians alike. Fear, respect, and ethical contemplation became intertwined with the reality of technological power, from mockery to mass destruction. The impossible weapon had permanently altered both the conduct of war and the collective understanding of what human innovation could unleash. The story of this weapon did not end with its deployment. Its influence persisted in post-war military doctrine, in technological research programs, and in the consciousness of those who had witnessed its power, from the frozen fields of testing grounds to the devastated streets of targeted cities. The arc from skepticism to operational dominance exemplified the profound impact of human ambition harnessed in pursuit of strategic advantage. The story of the impossible weapon is as much a testament to human ingenuity as it is a cautionary tale. What began as skepticism, ridicule, and theoretical debate evolved into a force capable of reshaping battlefields, altering strategies, and instilling fear across entire populations. It demonstrated the transformative power of science and engineering, revealing that with vision, persistence, and resources, even the most impossible concepts could become reality. Yet the weapon's legacy is not measured solely in technological achievement. Its deployment illuminated the moral complexities inherent in wartime innovation. Engineers and commanders confronted the unsettling truth that brilliance could serve destruction as readily as progress. Civilians, caught in its path, became a stark reminder of the human cost embedded within every calculation, every refinement, every launch. The duality of creation and devastation remains a central lesson. Ingenuity without ethical consideration can yield consequences that outlast the immediacy of battle. Strategically, the weapon altered the trajectory of warfare. It forced adaptation, spurred innovation, and accelerated the integration of precision, mobility, and psychological impact into military doctrine. Post-war technologies, from missile programs to rocketry, trace their lineage to the lessons learned under the pressure of necessity, urgency, and ambition. It was a turning point, not only in specific campaigns, but in the broader evolution of 20th century warfare. Above all, the tale of the impossible weapon underscores a fundamental truth. Human curiosity and ambition are unstoppable forces when channeled toward innovation. They can overcome immense technical challenges when untethered from moral restraint. They can unleash unprecedented destruction. The weapon's history, from derision to devastation, is a mirror of humanity itself, capable of astonishing achievement, yet shadowed by the costs that accompany such power. In the frozen test fields, in the smoke-filled ruins of targeted cities, and in the minds of those who witnessed its rise, The impossible weapon endures as both marvel and warning. Its story is a reminder that the boundary between possibility and peril is often narrower than we imagine, and that the pursuit of technological mastery carries with it responsibilities that extend far beyond the battlefield.